Today in pre-cal we started talking about harmonic motion, which is the applications of sine and cosine. The general formulas are f of t equals a sine b times t minus c plus d, and f of t equals a cosine b times t minus c plus d. In both of those, t equals time. This is applications where things are happening that are periodic, or sinusoidal is the word for that. And as I hope you've realized so far, anything that has the sine function could become the cosine function just by being shifted. So it's just a matter of deciding which something looks more like. We have 5 examples to look at, 5 cases, and your homework will very closely mirror this. So the first one is a grandfather clock. If I think about a grandfather clock, it's powered by the pendulum that swings on the bottom and the counterweights. And so if I think of the pendulum swinging, there's the pendulum, it swings this way first, let's just say. When the pendulum swings, that causes a sinusoidal motion. So I'm going to move out and then back to the other side and back, and that would be 1 period. So 1 cycle takes 2 seconds. Also, the maximum displacement is 15 centimeters. Remember, displacement means distance it went out. So 15 here, and then 15 back, 15 in the negative direction, and 15 back. I call this the positive direction, and this the negative direction. Okay, that information will be given to you in a word problem. Now that we have that, we want to graph it and find a general formula. So I'm going to start with the graph. If my displacement is 15, I could go 15 in the positive direction or 15 in the negative direction. My period is 2 seconds, so I'm just going to show 1 period. That's how far it goes. Half of that time would be 1, and we have some tick marks halfway in between. It takes 1 second for it to go out and back to the middle, and then another second for it to go negative and back to the middle. So in half a second it goes out, which means in half a second, we're going to start at 0. In half a second, it's at the top point. Half a second later, it's back at 0. So far we've done 1 out, that'd be up to 15, and back in to 0. Then we're going to go negative 15, and back to 0. And so if we draw a curve to fit that information, that curve most closely represents a sine function. So my equation is d, the displacement, that would be my y-axis, equals, and my amplitude is 15, my distance from the center up or down. That most closely represents sine. To find the new period, I have to do 2 pi over b, because I want to find b. The new period is 2. So if I want to solve that, I'm going to multiply both sides by b. 2 pi equals 2b, and pi equals b. So b is pi, that goes there, times t, the amount of time. There is no shift left or right, so that is all there is to that example. We've got an equation and we've got a graph, so we're good to go. The second example is dealing with the tides. Tides have a lot to do with life. In fact, they're part of what keeps our earth moving and going the way that we expect it to. When we talk about tides, we can talk about the low tide and the high tide. High tide is at 2.6 meters and low tide is at 2.6 meters negative, of course. When I'm talking about the time it takes to do that, it's 12¼ hours. That deals with how we move from the seasons, spring, summer, winter, fall. That's why it's not exactly 12. So basically the tides go in and out twice a day. Half of that time would be 6 1/8. We need to cut those in half as well. We want to start at low tide. The problem would give you that information, so just watch out for that. We're going to start here. Where we start, we also end. That's just by the nature of 1 cycle. Halfway in between, we would be in the middle. And that at our little marks in between those, we'd be at 0. This is modeled by a sine function. I'm sorry, not a sine, a cosine. And the reason is it kind of has that bell shape. Notice the difference in example 1 and 2 when I look at the graphs. This one is more like sine, this one is more like cosine. So if I'm looking to make an equation, I'm going to do y equals. My amplitude is 2.6, but this one is being reflected, so it is negative. We already said that the cosine was the most closely related relationship. And then we need to find the new period, which is 12 1/4 hours. So 2 pi over b equals 12 1/4. Excuse me. We need to find our b, so we can write it into our equation. Multiply both sides by b. 2 pi equals, and I'm going to make that a mixed fraction so that I can multiply by b more easily. 12 times 4 is 48, and 48 plus 1 is 49 over 4b. To get b by itself, I'm going to flip that fraction, multiply. Those cancel, and this side I have b. The other side I have 4 times 2, which is 8 pi over 49, and that's my b. People in class were a little worried about how big that value was and how different than a normal one it looked, but that's fine. That is what it comes out to. Think about 12 1/4 hour being just a little bit off as well. Okay, this one is not shifted up, down, left, or right, so that is my final answer of where the tide is at any time t. The third example we want to look at deals with electricity. And this one, we're going to start out with the formula, C of t equals 10 square root of 2 sine of 120 pi times t. In this case, part of what we're talking about is like the electricity in your house. This formula does show us that model. Let's go ahead and label the amplitude, which is 10 square root of 2. The period, which we can find by doing 2 pi over b. Our b is 120 pi. So if I simplify that, I get 1 over 60, and that's my period. In this problem, the thing I want you to be able to do is to tell me what the frequency is. Frequency is the same as 1 over the period. We know what the period is in this problem. So we've got 1 over 60, which is the same as 60 cycles per second. So that's the frequency. And that is the frequency of most homes. That's what's coming through your electrical currents when you're looking at that. And if you were an electrician, this would be something that you would need. Math really does apply in that case. The next example we want to talk about is a spring problem. I'm going to draw a desk or a table, or maybe your car in the undercarriage, and there's a spring coming from that, and maybe a weight on the bottom of it, or maybe not, just a spring. It is compressed at 20 centimeters. And every 8 seconds, it is moving back and forth. Plus or minus 20 centimeters. The science word for that would be oscillates. It's oscillating back and forth from the center. In this case, we start with it compressed. So we're going to draw our graph. Compressed means that this would be pushed up to the top of the table, so the spring is as smushed up as it could be. So 20 and negative 20. The time it takes is 8 seconds. The halfway mark would be 4, and then 2 and 6 in between those, respectively. And we're starting compressed, so we're starting at 20, we're ending at 20. Halfway in between, the spring would be unloaded as much as it possibly could be. And that would be our function. If we want to write a formula for this, our amplitude is 20. This most closely represents cosine. To find the new period, I'm going to do 2 pi over b equals 8, and solve for b. And that would be pi over 4 is b. And times t. That would be our time. If you put x there, that would be okay as well. Some people were concerned about the variable. That's a matter of your choosing, so do what makes you most comfortable as far as that's concerned. The final example that we want to look at, example 5, is a Ferris wheel. And we learned in zero period today that the Ferris wheel was made by a man with the last name Ferris, so we did a little research there because we were curious. In this case, I'm talking about a Ferris wheel. Oops, it's a little bit off the ground. Sorry, my pen got away from me there. So you've got this circle. From the center to the bottom of the Ferris wheel is 100 feet. And the distance from the center of the Ferris wheel to the ground is 105 feet. So basically there's a 5-foot distance from the bottom of the Ferris wheel to the ground. We wouldn't want the people scraping their bodies against the ground surface, so that's important. One rotation happens in 30 seconds. So this is a very fast, fun Ferris wheel. we need to go ahead and draw our graph. And in this case, we are going to have a shift upwards. 5 feet off the ground is the lowest point the people will be in the Ferris wheel. Then 100 feet up from that would be 105. That would be in this middle point. And at the highest, they'd be at 205. In the problem, I told you in class that the person is right here, and everybody worried about him being in a basket. He's in a basket. I just drew him right here to show you he's at the midpoint, and he's circling in the counterclockwise direction. So that's not where he started. Obviously, he started at the bottom where he got into the Ferris wheel, but the time that we start watching him at time 0, he's in the middle. So I'm going to go ahead and put a dot in the middle at time 0. A full rotation takes 30 seconds. Half of that would be 15. The mark's in between. At the end of the time, he would have one rotation. He'd be back at the middle. Halfway through, he'd be at the middle. At 7.5 seconds, he'd be at the top. And at 22.5, he'd be at the bottom. So we've got our Ferris wheel there. Okay, let's look at an equation. So y equals, the amplitude is 100, and that's because that's the distance between 105 and 205, or 105 and 5. That's amplitude. This most closely is represented by sine. Our new period is 2 pi over b equals 30, or b equals pi over 15. You could work that out if you need more help. I can show you that when you get back to class. Times t, our time. And then this one is shifted up. And if you're struggling with how to shift that up, think of where you would move the 0. The 0 is the middle mark, so 0 is now 105, so this is being shifted up by 105. And that's the end of our notes today. You do have an assignment that's like each one of these. If you have questions, let me know.